Hello, everyone. It's 3:10, so we're going to start. Today, we are happy to have Professor Stefan Williams from University of Sydney. He is the head of School of Aerospace, Mechanical and Mechatronic Engineering and Professor of Marine Robotics at the University of Sydney. He is a member of the Australian Center for Field Robotics, where he leads the Marine Robotics Group and is the head of Australia's Integrated Marine Observing System Autonomous Underwater Vehicle Facility. He was president of the Australian Robotics and Automation Association from 2014 to 2016, and in 2018 was recognized as a distinguished lecturer by the IEEE Ocean Engineering Society. His research interests include simultaneous localization and mapping in unstructured underwater environments using visual and acoustic sensing, autonomous navigation and control, and classification and clustering of large volumes of data collected by robotic systems. He received his PhD from University of Sydney in 2002 and completed a Bachelor of Applied Science in Systems Design Engineering at the University of Waterloo, Canada in 1997. You may ask questions during the talk by writing them in the chat or raising your hand, or just wait until the end of the talk. So Stefan, it's all yours.
Okay, thanks, Coral, and thanks to Coral and Nicole for organizing today and for the invitation from University of New Hampshire to speak with you this morning, or this afternoon, I guess, for you guys. Gives me a great pleasure to talk to you today. I'm going to talk a little bit about some of the work that we've been doing over the past 20 years in developing autonomous underwater vehicle systems, thinking about how we can use these sorts of systems to inform a variety of different scientific outcomes. I'll show some examples of the kind of work that we've done looking at aspects of navigation and mapping, control planning, and some of the data analytics that we do with the data that we're collecting. So just as a little bit of background, I work, as Coral said, at the Australian Center for Field Robotics at the University of Sydney. This is a center that was founded over 20 years ago and has really been focused on conducting fundamental and applied research in robotics across a broad variety of domains. We have about 130 staff and students working in this area. And it's one of the largest field robotics intelligent systems groups in the world, with a significant annual budget, the majority of which is actually sourced from direct industry partnerships. So we work very closely with a variety of stakeholders, looking at aspects of field robotics in aerial, ground, and the marine domain. We've worked closely in areas such as mining, stevedoring, transportation, logistics, number of defense pieces of work. I'm going to focus today primarily on our marine robotics program, but there's a lot of other work that's going on across the center. This sort of video montage just shows a few of the examples of the sorts of things that we're working on. The top left is an example of an aerial, unmanned aerial docking demonstration that we did, where we had a couple of unmanned air vehicles flying simultaneously, working together on a joint control system. We've got a big flight test facility a couple hundred kilometers south of Sydney. We do a lot of work in agriculture in the top right. This is an example of some work that's now spun out into a commercial startup, looking at high precision agricultural applications. So how we can take concepts in robotics and really apply them on large scales to farming and horticulture, as well as a number of other agricultural areas. Do a lot of work on autonomous ground vehicles and intelligent transportation systems, and we're part of an iMove cooperative research center, which is really looking at the future of transportation systems. And finally, we have a very large partnership with Rio Tinto, looking at mine automation, and their Mine of the Future program is predominantly supported through the ACFR, and has been a over decade-long partnership in this area. Mining is a big industry here in Australia, and we've enjoyed a significant amount of support in that area. I could probably talk for an hour about each of these areas, but I'm going to focus today predominantly on our marine systems program. And our main focus over the last while has really been on areas of platforms and sensing, so developing autonomous platforms, sensing, looking at hyperspectral and light field imaging in the context of underwater deployments. We've done a lot of work on navigation and mapping, so simultaneous localization using both visual and acoustic data, a lot of work on planning and control, thinking about multi-vehicle deployments, that sort of thing. And a lot of our work recently is really focused on the data analytics. So how do we take the data that we're collecting and turn it into information that's useful for science, and working with a variety of partners in this area. We consider applications not only in the engineering sciences, so the fundamental contributions to these AUV systems, but also looking to support work in ecology, archaeology, and some geoscience work. And I'll talk a bit about some of these sorts of applications throughout the course of the talk. And as with a lot of scientific endeavor, we work with a large group of both Australian and international collaborators. As Carl mentioned, I've been fortunate to be part of the Australia's Integrated Marine Observing System program, which has been running for nearly 15 years now. It's funded through something called a National Collaborative Research Infrastructure Scheme. And this is a program run by the federal government that provides support for infrastructure for sciences that are designated of national importance. And marine science is one of those areas. The marine estate for Australia is very important until last year, I guess. Tourism has been a huge part of Australia's economy, and a lot of that relies on aspects of ocean and Great Barrier Reef, and a lot of people come to Australia for those reasons. Borders are closed at the moment, so that's a little bit of a challenge from that point of view. But there's certainly been a lot of investment in infrastructure to support the marine sciences. And AMOS supports fleets of gliders, Australia's contribution to Argo floats. We instrument ships and have a mooring array that's deployed around the country. And we operate an autonomous underwater vehicle facility associated with this program. So we provide access to scientists to AUV systems and deploy these at sites around the country with a view to really characterize change on sensitive reef habitats and linking these to oceanographic processes and changes in climate. So this little figure shows basically an overview of the deployments that we've done over the past nearly 15 years now. We've really worked across all around Australia, from the tropical north all the way down into more temperate regions in the south. One of the key features of this program has really been our ability to go back to sites on an annual basis or semi-annual basis to help scientists understand change through time in these habitats. The colors of the little dots correspond to the dominant habitat types. So you can see in the north, we have extensive coral reefs. And then as we get down further south, we're looking at the transition between coral and kelp, and also doing some work down into deeper water canyons and sessile invertebrate dominated habitats. We've also done a lot of work, as I mentioned, with international partners. So we've worked all around the world looking at supporting science in ecology, archaeology, and geoscience. And in Australia, we've had our main focus has really been on ecology, but we've really worked across these other domains. We've done a lot of work in Japan and in the Mediterranean and throughout the Caribbean and the US. And we work with a variety of different platforms. So we have our own AUV systems, imaging systems that we bring to deploy with partners. We've worked with the Woods Hole Oceanographic Institution quite closely on a number of deployments. We work with colleagues at the University of Southampton, University of Tokyo, and a variety of other institutions. A lot of our early work focused on navigation and mapping, so our ability to take large volumes of stereo imagery collected by our AUV systems and to stitch it together into detailed models of the habitats that we were surveying. So this is an example of some work done in Tasmania. Here we've taken the vehicle has covered a bit of near the foreshore, actually looking at what once were kelp-dominated habitats, which have been extensively affected by urchins and have turned into extensive urchin barrens. But what you can see here is a three-dimensional model that's been derived by the AUV data. So the transect you can see running sort of from the right to the left is the vehicle transiting in from about 35 meters up into very near shore environments. Then mowing the lawn to do a dense cover of a particular bit of the foreshore. If I zoom in on that, you can see the boulder field with sort of remnant kelp sitting on top of it. And we can do a texture mapped overlay on these three-dimensional models. These are resolved down to sort of millimeter pixel resolution. And we can use this sort of data. As I said, we've got these extensive urchin barrens which are developing around us, around Tasmania. And one of the things that our partners are really interested in is not only the long-term trends, which are showing significant increases in these barrens to the point where I think 15 to 20% of the Tasmanian coastline is now dominated by these urchin barrens, where it would have been kelp dominated 30 to 40 years ago. But they're also interested in the temporal behavior of these urchins. And here's an area of boulder field that was surveyed during the day. We've then come back at night, repeated the same area, so we can actually take our robots back to the same bit of the seafloor. And if we kind of zoom in on a bit of this model, we can see that the urchins, which during the day sort of hide out in the crevices, so you can, if you look carefully, you can actually see them hiding out in amongst the rocks. They come out at night and they actually feed on algae and essentially prevent the kelp from reestablishing itself. There's been some studies looking at the introduction of large lobsters, which can help to control these urchin populations, but a lot of this is actually linked to changes in the climate and the fact that the waters around Tasmania are warming as fast or faster than almost anywhere on the planet because of changes in the dominant current fields around Australia. We're also interested in change across much longer temporal scales. So this is some work we did in Western Australia, looking at a significant warming event along the West Australian coast. So the graph here shows the long-term monthly average sea surface temperatures over the 50-year period, and then the in situ measured daily average in late 2010, early 2011. And we'd done some surveys in 2010. We came back in 2011, just on the tail end of this significant warming event. And what we could see was extensive bleaching occurring along the West Australian coast. So here you can see a bit of a survey of one of the areas that we did, where this plate coral has bleached extensively between 2010 and 2011. And then we've repeated those, and actually we just completed the 2021 surveys of these sites earlier this year. What we can see is that the plate coral is bleached extensively, it's died off, but you can also see that these branching corals are growing quite aggressively into the space vacated by the plate coral, which is died. And so we can use not only this sort of imagery, but also the three-dimensional structure to really characterize change in the habitat complexity. And in fact, over the 2010 to 2013, we can actually see a significant increase in habitat complexity resulting from a change from plate coral dominated to this branching coral, which seems to be growing much faster. And so we're able to provide this sort of information, both the imagery and the three-dimensional structure, to scientists who can then study changes in these reefs at a sort of unprecedented level of detail and across a variety of different water depths. We're also working with colleagues who are interested in mesophotic reefs down in the 40 to 50 meters, where it's quite difficult to get on scuba. So using robotic systems really provides a unique insight into these sorts of habitats. Done a lot of work looking at the impacts of cyclones also. We've seen increases in the number of cyclones along in Australia's tropical north. And in 2014, we were scheduled to actually do some surveys around a place called Lizard Island up in the far north of the Great Barrier Reef, which was impacted. Actually, the cyclone went straight over the top of the island. There's a resort on the island which was destroyed and took a number of years to rebuild. There's also a scientific research station. So my team were able to get up there immediately following the cyclone and surveyed reef areas around the island with a view to characterizing recovery after this cyclone. Unfortunately, Lizard was hit by a second cyclone in 2015, and then extensive bleaching occurred along the Barrier Reef in 2016 and 2017. So the story is much more complex than we maybe originally anticipated. But what we've done here is we've used both robotic systems, but also taken a diver-held imaging system where we put a little stake in the middle of our survey site. We wrap a line around a drum on the top of this stake, attach that to a camera, and then we get divers to sort of swim around. And as they go, the line unravels, sort of like an old record player. And we end up with very repeatable surveys of these order 100 to 130 square meter plots. We call these a reef record, in reference to sort of old style vinyl records, where we're basically swimming from the middle out, then completing a couple of transects. We can then use the stereo imagery to reconstruct the location of all of the images. And from that, we can then build these sort of detailed 3D models of the reef structure, which you can see here, hopefully that's coming through. So you can see a lot of detail in here of not only the texture, but also the 3D physical structure of these reef sites. And we can do this on an annual basis. So we've been back, we started with 6 monthly surveys. I should actually update this slide because we've now had a team up there earlier this year as well, doing surveys in 20. So we've got surveys from 2018, 19, and we didn't do 20 because of the coronavirus, but we did manage to get up there in early 2021. And we've repeated all these sites around the island. What we can do is then sort of look through time at how these reefs are reacting to both cyclone and bleaching activity. So here's an example of a bit of reef in 2014, immediately following that first cyclone. In 2015, following a second cyclone event, you can see we've lost a fair bit of the coral cover. And then in 2016, it's really been completely wiped out. And in fact, there's a lot of algae growing on these remnant reef structures. And the arrow just points to a particular structure. You can kind of reference, what's changed through time. This is another bit of one of these survey sites. So you can see 2014 looking reasonably healthy here. 2015, not a lot of change. 2016, a lot of this acropora really is bleached, and you're seeing a disappearance of the color. And another part of the island in 2014, 15 is actually looking pretty healthy, and 17 here, this is another bit of the island. So there's a lot of interesting dynamics happening around this island, lots of different areas, part of which are exposed to wave-dominated impacts. And then we can look through 2016, 17, 18, where there was extensive bleaching along the full extent of the Great Barrier Reef. And in 19, you can actually see a lot of recovery. So there's a lot of new recruits starting to grow. And it looks like 2021, the story is sort of similarly positive in terms of the return of the coral in this part of the Barrier Reef. And again, another bit of a bit of reef structure. And you can really see strong recovery. So I think it's really, using these sort of imaging techniques, whether it's with a diver or we've also used robotic systems around Lizard to collect some very large scale plots, allows our colleagues to really characterize change at the level of sort of individual colonies and down to sort of looking at new recruits that are growing. We can also look at change over much longer time scales and think about the predicted changes of the impacts of climate change. So here we've got sites that have been surveyed by the AUV along the southeast corner of Australia. So this is New South Wales and Tasmania. They've taken sites along this coast, looked at characterizing where they see particular sessile invertebrates in particular here. So these are sponges and ascidians and things like that. They've characterized where they are seeing these. They've also used climate models, which are predicting sea surface change in temperature between the 90s and 2060s. And then have used these forecasts to predict changes in the distribution of these particular organisms, and in fact are predicting a poleward shift of a lot of these sorts of organisms. And we're seeing similar things in the tropics as well, with the tropicalization of some of the waters along the New South Wales coast. So we're seeing coral reefs starting to be established in Sydney Harbour. And I think a couple of years ago, we saw some evidence of bleaching in Sydney Harbour, which is highly unusual. So really using the data that we're collecting to inform models of habitat distribution and then climate models to predict forward to what might happen in the future. I think it's some pretty interesting science that's being supported by the data that we're collecting. I also do a lot of work on planning and control. So we think about how to get these vehicles operating in close proximity to the sea floor. So this is one of our main platforms. This is the AUV Sirius. It was developed at the Woods Hole Oceanographic Institution, but we've been operating this vehicle since 2005. It's gone through a number of upgrades and sort of enhancements, but effectively we fly this vehicle at about 2 meters altitude. This video is showing the vehicle operating at a site in Greece called Antikythera. So this is the site of a 1st century BC shipwreck. We were asked to come and map this site by Woods Hole and the Greek effort of antiquities. And in the background is the location of this this wreck site. But you can see the vehicle operating very close to the sea floor, taking multiple stereo images while it's underway, and we stitch those together into these habitat models. And I'll talk a little bit more about the Antikythera program in a little bit. We're also thinking at the multi-vehicle deployment. We had some work supported by the Schmidt Ocean Institute in 2018. We had a chance to do some deployments around Hawaii and invited colleagues from Hui, MIT, Rhode Island, and the University of Michigan to bring all their toys. And so we had multiple AUVs, drifting imaging floats, gliders, and a prototype of a surface vessel. And one of the challenges here was really deploying multiple platforms simultaneously from the ship and sort of managing these things. In the bottom, you can see a little Gantt chart that we were keeping track of where and when all of our assets on the ship were being deployed, and thinking about, multi-hour deployments with the gliders and multiple floats and AUVs being deployed. Of course, it's not one person to many vehicles. We had a large team supporting these activities, both ship crew as well as science partners. And this sort of montage is meant to kind of capture a day in the life on board. We had teams out deploying the gliders and the imaging floats. We had AUVs being deployed from the ship. Up on the bridge, we had a map-based interface, which was used, and all of our platforms being tracked in real time and being plotted up on this this visualization of where the ship was, where all the assets were. And that was a really important communication tool for us between us and the ship's crew, and all of the teams that were deployed out in the field deploying various assets. So a lot of thinking about the logistics of multi-vehicle operation. Brian Williams from MIT and some of his students were along, and they were doing some work on risk-aware planning tools, which they originally deployed in collaboration with NASA, but thinking about, how do we ensure that we get all our assets deployed and recovered, and sort of modeling the interrelationships between where the ship might be, where some of the smaller support vessels were, and where we had instruments in the water, and automatically looking for negotiating conflicts and goals between the teams, and making recommendations on when and where to deploy different assets. We did have one situation in which one of the PhD students came up and said to me, we're going to run out of time here. We're not going to be able to recover all these assets in time for dinner. And sure enough, we ended up with gliders surfacing somewhere where we hadn't quite expected it, and a couple of AUVs off in another segment, and having to negotiate with the ship's crew around the start of dinner in order to get all our gear back on board. So I think having these sorts of tools and thinking about how we can support multi-vehicle operations is an interesting area of future development. We've also been thinking about planning in the context of probabilistic habitat mapping. So I know that UNH does a lot of work in multi-beam bathymetric mapping. We've been doing work in taking some of the outcomes of those bathymetric mapping efforts and looking at deploying AUVs to most effectively learn habitat models. So what we do here is we take the AUV transect shown in red. We get bathymetric patches, and we use a bathymetric autoencoder to find a latent space that describes the sort of structure of the seafloor that we're seeing. We also use an unsupervised clustering technique to look for imagery that is sort of characteristic of these environments. And from that, we can generate a distribution of habitat labels and automatically learn relationships between the underlying bathymetry and the imagery that we're seeing in the AUV, collected by the AUV. And what we're thinking about is how do we use this sort of information to plan future dives to most effectively improve the quality of the model that relates that underlying bathymetry to the visual features that we're seeing. So from this sort of automated process, we end up with a number of different classes of habitat, and these are unsupervised but subsequently labeled. We can then take sort of these colors and plot them against the AUV sites, and then do that prediction. So we're predicting out where we expect to see this sort of habitat based on the bathymetric structure. In addition to those predictions, we can also look at the uncertainty in the underlying models. So the top two figures here are two different characterizations of uncertainty in the model. So the aleatoric uncertainty effectively is a measure of entropy. So it tells us how uncertain the model is about what we might be seeing. And in areas of flat topography, we might see something that's dominated by, there's an invasive species of it's called a screw shell, which is a type of snail. And it's very hard to distinguish that from just flat sand in the bathymetric data. Other parts of the reef or other parts of this survey area are dominated by reef. And this epistemic uncertainty tells us something about not the uncertainty in what we might see, but the uncertainty in the model parameters. And this is more important for us in characterizing where we should go next in order to improve the model parameters, because there are some areas that from the bathymetric data, we may not be able to distinguish what we would expect to see visually. But as long as we're sure that we're uncertain, I think that's that gets us much closer to a model that tells us something about what the habitat's characterized by. And we can use this sort of information, these different types of uncertainty, to drive choices about where to deploy the vehicle next to increase the model prediction fidelity more quickly. And if we use this epistemic, so the uncertainty in model parameters, we much more quickly converge to the validation accuracy that we would get over longer periods by using all the data. So we're using sort of these data-driven approaches to think about where we should deploy vehicles to improve model performance. I think there's some key challenges with planning. There's a lot of uncertainty in the real world. Things like weather bathymetry currents are often difficult to characterize. We often don't have access to very informative priors. So, bootstrapping these models is another thing that we're looking at the moment. Framing problems at a suitable level of abstraction that they make sense in the context of the science that we're trying to support. And I guess jointly planning vehicle dives and ship locations. There's a high dimensional space in which some of this planning occurs, and so it's still lots of interesting research to be done in this area. As I said, we collect a huge amount of data using these sorts of platforms, and all of our data is available online through online archives with tens to hundreds of thousands of images being collected with each deployment. We've got in excess of 5 million seafloor images now in archives, which are all fully available online. And we've got a project now which is starting to capture the labeling, which is being done by our science partners, and making that also available so that people can actually get not only the imagery, but also the associated labels that have been generated with that data. And from that, we can start to think about both unsupervised clustering techniques. As I mentioned, we're using this to, in a fully unsupervised way, build habitat models, but we can also use labeled data to train classifiers to identify particular bits of the seafloor in high detail. One example of this is one of my PhD students who's just finishing up. He's been looking at characterizing the site affinity for different mobile organisms. And in this case, this is an example of lobsters. So he's trained a convolutional neural network to find lobsters, used the AUV imagery to build these 3D reconstructions, done a spatial projection of the lobster detections, and then plotted those on the underlying three-dimensional model. And we can then look at derived data products like population density and terrain rugosity, and start to think of of how the terrain structure is informing where these lobsters occur. So these are some examples of the sort of imagery that we've got, and the detections which are being achieved by these neural networks. We can then look at the detected locations, the heat map, which is sort of where they're located, and relate that to the rugosity. And we can see that a lot of these lobsters are hiding out in areas of relatively high rugosity. They kind of get in under crevices and things like that, which is something we'd probably expect, but being able to do this with the sort of resolution that we're achieving, I think is allowing us to do some interesting new science. We do have to be a little bit careful with this because our neural networks aren't infallible. So these are some examples on the top row of true detections, and at the bottom, these are sponges which look somewhat lobster-like. So there's still a bit of work to do in getting these sorts of models to translate across different data sets and to deal with a richer vocabulary of target species. So some of the challenges with this data analytics is consistency in labels across environments. We have lots of people looking at this imagery. They all like to call things slightly different things. So we're looking at schemes that allow us to translate between different labeling. We have relatively small amounts of labeled data. So using both unsupervised techniques and dealing with unbalanced data sets, transfer learning, multimodal learning, all of these sort of areas of future work that we're exploring. But as some of my colleagues like to say, one of the most significant challenges in marine robotics is ensuring that the number of deployments equals the number of recoveries. When you put equipment into the water, you want to make sure that you can get it back. And there's a lot of effort that goes into tracking these vehicles, ensuring that they're coming back safe. And weather can play a huge role in this. So these two images in the top left and right here show a bit of the Bass Strait, which is a bit of water between Tasmania and the Australian mainland, which is notoriously rough and often looks like what you see on the left. But we've also had deployments there which have been like a mill pond, just glassy, and so being prepared for these sorts of situations is pretty challenging. We have had situations where the vehicles have experienced pretty rough recoveries, coming in, getting broadside to waves and having the vehicle on the end of a crane. We have bounced this vehicle off the sides of ships a couple of times. This was one example in Tasmania. The vehicle sustained some pretty extensive damage, but with some buckets and a bit of chewing gum and sticky tape, we were able to get the vehicle back into shape and deploying again the following day. Of course, once we get back to the lab, there's more extensive repairs would be undertaken. In Antikythera, we did 2 field seasons there in Greece. This is a location that's sort of between an island of Kythera and Crete, and a team from Woods Hole invited us to come along and help map this site, which was originally discovered in the early 1900s, but the team were interested in characterizing this site in more detail. So we went down, we surveyed in our first season about a 10,000 square meter area of seafloor. We could see artifacts, the camphora, the part of the anchor stock and pottery shards. And these models were actually used by the dive teams to plan their dives. So this is an example of a 3D model. This is, here is a lead anchor stock. So this would have been part of the ship's anchor. And you can see that transition into the divers actually going down. This site's about 60 to 70 meters of water depth. Fantastic opportunity for us to be involved in some really exciting archaeological examinations, and the maps that we generated were used to plan future deployments of future excavations. And in fact, the team discovered a nearly complete skeleton on the site buried under the sediment. So this is a skeletal remains that have been buried on the site since I think about 83 BC, so over 2,000 years. So really exciting to be part of this. We were operating in quite close proximity to the sea floor. Some of the days were pretty rough out there. And in the second field season, we came back and the team were interested in us mapping a much more extensive area of the sea floor. So we were able to do the majority of this. And in fact, they were able to document artifacts at 2 sites. And one question was whether this was a single wreck sort of strewn across this quite large area of seafloor, or 2 wrecks. And it looks from this sort of distribution of these artifacts that it's likely to be 2 wrecks on this site. But we can't always trust this data. So we had been given this underlying bathymetric map, and we'd planned out some dives. And this little line here is a cliff that goes from about 60 meters down to about 70 meters, so about 10-meter drop off. And we planned our initial dives to be well clear of that cliff. We deployed the vehicle. It went down, followed along the seafloor. We acoustically track the vehicle. We get some status updates, and we saw it drop from about 60 meters down to 70 meters, turn around and come back. And then it just stopped. We thought there might be something, that was struggling to get up this cliff, because we knew this was here. But you can see there's an offset here of it was about 5 to 10 meters. We thought we were well clear of that cliff. Turned out that there was a registration issue between our navigation and the underlying bathymetry we'd been given. So the vehicle had driven off the cliff, gone down, turned around, and started making its way back up. We acoustically aborted the vehicle, and it sort of rose a little bit, but then just stopped. And this is data that, following our subsequent recovery, we were able to see where the vehicle had got stuck just along this cliff face. We did have an ROV along, so we popped that in the water, drove it down, quickly located the AUV, and could see that it was actually stuck at the base of this cliff underneath a fishing line. So that's the fishing line. Somebody's lost their fishing gear on the cliff. So we sort of looked at this, thought, how are we going to get this vehicle back? We've moved the ROV into position. So there's a lot of head scratching going on here, thinking, all right, how are we going to fix this? I've driven the vehicle, the ROV up, grabbed the vehicle's antenna. So this is sort of an ROV recovery of an AUV. We've then driven the ROV down to free the vehicle from the fishing line. And then we're able to sort of pull it out and allow the vehicle to float back up to the surface. Yeah, so we were reasonably fortunate. We did have another incident in the second field season where the vehicle again got entangled in fishing lines. So this is, a bit of a risk, and we use a lot of safety systems. We bring along ROVs to allow us to deal with these sorts of situations. And of course, there's that lonely day when, despite all the hard work, preparation, safety briefings, etc., things just go wrong. So a number of platforms around the world have been lost. Some have imploded at depth. Some have ended up under ice. Some have just not performed for a variety of reasons. There's ship strikes. There's a lot of sort of logistics that go into ensuring that we get our gear back. We had an issue with our AV, and this is about 10 years ago now. And we'd done a week of work. We This is actually a picture that I took from the shore. I was heading back to Sydney for a graduation ceremony. The team were going to do one more day of ops. They deployed the vehicle. It did its mission. It rose to the surface, finished its mission, and promptly sank to the sea floor. The skipper then said, well, we have no fuel left. We can't stick around. So they left the site. We do have a drop weight that drops off, and the vehicle presumably surfaced. We talked to and when they got back, the vehicle was gone, and we couldn't acoustically find it again. We talked to the water police, who said, "Oh, it's kind of the winds coming from the south, from the north. It's probably going to drift south." We had colleagues who are oceanographers telling us that the currents were tracking north, so it would probably go north. We did a lot of acoustic searches over a couple of days. We got ships and a variety of vessels and aircraft looking for the vehicle. After a couple of days, had to give up, but we were extremely fortunate that about 2 weeks later, I was sitting on my back deck having a beer, thinking about what to do with my career now that I'd lost our AUV, when I got a call from some journalists who said, actually, your AUV is washed up on the shore about 100 kilometers north of where we'd misplaced it. So I was on the next plane up to the Sunshine Coast, recovered the vehicle, and within about 2 months, we were back in the water with our operational program. So very fortunate. And I guess, in reflection, there's been some phenomenal successes from marine robotic systems and programs around the world. So, a lot of the discovery hydrothermal spreading centers are being supported by this sort of technology. Lots of focus on understanding life in our oceans and new life forms, cost-effective in situ validation of satellite observations, and of course, exploring the deepest parts of our oceans, relying extensively on these sorts of technologies. And of course, this work can be very rewarding and a whole lot of fun. I still get out in the field occasionally, and was actually in Tasmania a couple of weeks ago, conducting these sorts of surveys, and I really enjoy this sort of work. So if I reflect on sort of key challenges in platforms and sensing, I think we're sort of at a point where vehicles and operations are pretty reliable. We can operate in fairly difficult environments, although turbidity, low light, and high altitude operations still are challenging. We can coordinate developments, cooperative deployments where we have multiple vehicles working together is something we still have work to do. A lot of our online navigation and post-dive SLAM are quite solid and well established technologies. We don't actually run the SLAM online, and there's a bit of engineering to do there. In terms of planning and control, I think the low-level aspects of this are quite robust. We do a lot of manual dive planning, but automating cruise planning and taking those notions of model fidelity into account, I think is interesting. And a lot of work on the data analytics and turning, a huge amount of raw data into information that informs science, I think is something that's a big focus for us. And of course, we have a strong focus on stakeholder engagement and applications and understanding requirements and delivering data, and transforming that data into something that can be used to support a variety of different scientific inquiries is something we continue to work on. Looking forward, I think we've got some interest in long-range autonomous marine teams. We're thinking about intervention. So we're working with a small startup here in Sydney who are developing small underwater manipulators, and one of my PhD students works there part-time, and so we've got a good collaboration going with them. Long-range AUVs, I think we've seen a real transformation in oceanographic sciences from the Argo float program, and a lot of interesting work going on to really move away from that paradigm of a ship tending one or multiple AUVs to AUVs being deployed for long ranges and being tended remotely. And some really exciting work coming out of Mbari and Southampton and various other groups around the world. And some of this might be supported with surface vessels, and there's some real examples, some real successes here with companies like Saildrone and the Wave Gliders having done some really phenomenal deployments over huge spatial extents. And so I think thinking about teaming in the context of this kind of work is really exciting. So I think in conclusion, marine robotic systems present novel tools for collecting rich and high-resolution georeference data sets. I think managing that data, transforming it into data products is a key challenge. And I think for us, engaging with a variety of end user communities is really providing us with a lot of motivation for the work that we do, exciting opportunities for our students to get involved in some really cutting edge science, and also drives our own engineering sciences and the things that we're thinking about. So the future challenges include long-range autonomous marine teams, AUV and unmanned surface vessel design optimized for particular mission objectives. There's a lot of potential in machine learning for visual and acoustic data and the combination of multimodal learning. And really increasing the operational tempo of these sorts of systems is a big area for future work. And we're always looking for PhDs and postdocs, and have some exciting work, not only in the marine area, but also in areas of mining, agriculture, UAVs, etc. I'd be certainly happy to hear from anyone interested in potentially visiting us here in Australia once our borders reopen, which are unfortunately still closed, but as we manage our coronavirus response. But would certainly welcome opportunities to work with people and think about collaborative opportunities. And of course, I have to thank a huge network of support that's facilitated this work, and a huge team that sits behind all of this. So thanks for that, and I'm happy to take some questions.
Thank you so much, Stefan. Very exciting work and wonderful talk. So if anyone has any questions, then please feel free either to write that in the chat window, or Willard, do you have a question?
Well, I was very interested in that little bullet point there that was skipped over about autonomous intervention. Could you perhaps say a few words about that and what you mean by it?
So autonomous intervention. So when we're thinking about that, we're thinking about these sort of manipulation and interaction. So a lot of the work that we've done really is sort of passively observing the environment. Is just sort of taking images or multibeam data, stitching that together into models of the environment. What we'd really like to do is think about, okay, how can we use that model data to actually go in and interact with the environment? So whether it's in an industrial application, thinking about operation around oil and gas platforms, for example, or in scientific endeavor, really being able to say, okay, there's a thing that we're looking for, let's go in and pick that up. So we're thinking about taking a lot of the work that's going on. There's a lot of work on mobile manipulation in terrestrial and home environments, translating that into very challenging environments. There's a lot of perceptual challenges. There's a moving platform, so you don't have a stable base. So there's a very tight coupling between the platform and the manipulator, being able to sort of reliably recover objects of interest, or manipulate valves and things like that. So there's a lot of interesting work there in sort of optimizing the intervention itself. And this little team here in Sydney who are building these manipulators are working closely with us. So they're all electric manipulators. They've got a couple of sizes. One sort of small scale and it can be operated from relatively small ROVs, but they've got a larger sort of person size manipulator now that they've brought to market, and we're working with them on sort of developing some more autonomy capabilities with those manipulators.
I actually have a follow-up question on that. So what kind of approach would you take to do such autonomy? For example, have you considered the reinforcement learning approach? I mean, I know that recently in the deep reinforcement learning, they applied that to manipulator arms, and with that regard, there has been pretty, I mean, it's kind of funny to say extensive work, but relatively to this field, like applying deep reinforcement learning to robotics, they've been applying that a lot, quite more to the.
Yeah, we haven't yet got to the reinforcement learning, but I think that's probably sort of a next step. A lot of the work that we've been doing now is looking at techniques for disturbance rejection. So looking at how we can, if the vehicle is being moved around, how can we ensure that the manipulator, the thing that we're interested in, is stable even in the presence of those sorts of periodic disturbances. We've also been doing some work on optimizing the wrench or the amount of force that we can apply through the manipulator. And in fact, the student who's doing a lot of this work was looking at optimizing that wrench, and it was so effective that he actually destroyed a couple of the arms because he was able to apply so much force through some of the joints that that they actually failed, which I think was good for the company to know that that I think they've done a redesign of one of the joints to sort of mitigate against that. But so that's more sort of analytical and more traditional control techniques that he's using to do that kind of optimization. But I think the reinforcement learning and deep reinforcement learning is certainly something that that has a lot of potential in this context.
Yeah, I'm actually applying that to autonomous surface vehicles. So just curious.
Perfect.
Are there any other questions? Nope. Okay, so with that, it's 4 p.m. and we will wrap up the session. Thank you everyone who joined us this semester and year. Hope you have a fun and enjoyable summer break, and good luck with the exams. And thank you so much for joining us, and thank you, Stefan, for joining us, especially at such early hours. And wishing you to enjoy the weekend.
Yeah, and thanks for the opportunity, and look forward to seeing everyone in the future. Thanks.